So now I'm trying to cover the topic energy stored in an inductor and energy density. Okay, so we already know that if suppose there is a inductor and if current is flowing through it I, if there is a change of current, then there is a induced EMF in it due to its own change of current. So the induced EMF is given by minus L di by dt, where di by dt is representing the rate of change of current. For a derivation of energy stored in inductor, this negative sign is not required. We will just take the mod of it. Hence we can write sigma equal to L di by dt. If I multiply both side I, so now sigma into I, it is like power, right? Sigma into I, that is power. Power equal to L I di by dt. And power we can write du by dt, rate of change of energy. Now this di by dt is not required, so simply we can write du equal to Li di. Now we can integrate both sides. When the current in the inductor is 0, that time energy is 0. If current in the inductor reaches the value I, that time energy stored in inductor is U. So integration of this side is U and L. Integration of this side is going to be I square upon 2. So our formula is half Li square. So energy stored in an inductor is how much? Half Li square, where L is self-inductance of the coil. L is self-inductance of coil or solenoid. And I is the current, that is obvious, U. Now what about the energy density? Where does this energy get stored? So as there is a flow of current, then it generates a magnetic field inside it. That magnetic field remains almost constant inside it. So there is a space inside this solenoid. In that space, it stores the energy in form of magnetic energy. The energy density stands for energy per unit volume. Energy per unit volume. Energy density. Energy density is equal to energy upon volume. The energy is how much? Half Li square. And the volume is A into L, length. Area of cross section into length. Here A is the area of cross section. Area of cross section. And L is the length of the solenoid. L is the length of the solenoid. Length of solenoid. And the L, that is called self-inductance. L is here self-inductance and its value is mu naught N square L A. That already I have done earlier. So it's a time to put the value. And there is a relation between I and the magnetic field. And the magnetic field inside is given as B equal to mu naught Ni. So the value of I is B upon mu naught N. So let us put all the value here. Then half L is how much? Mu naught N square A L. And the I is B upon that. So this will become B square upon mu naught square upon n square upon volume A L. So this A L will cancel out, this n square cancel out, and this 1 mu naught cancel out. Then we are left with 1 by 2 B square upon mu naught. Now we can compare this with the capacitor. If you have a capacitor and the energy stored in it is how much? Half CV square. The energy stored is there half CV square. Because a capacitor stores the energy in form of electrostatic energy. If you compare, here the energy stored is half L square. So half is same and C is replaced with L and the I is replaced with the V. And here energy density in case of capacitor, energy density is half epsilon naught E square, where the value of E is the value of electric field. So it is also similar to that. Here it is like half, and instead of epsilon naught, here it is 1 by mu naught and into B square. See, in electrostat, the constant is 1 by 4 pi epsilon naught. And in the magnetism, the constant is mu naught upon 4 pi. Mu naught upon 4 pi. Where mu naught is called permeability of free space, epsilon naught is called permittivity of free space. So in electrostat, it is on the downside, it is in the this denominator side, and this mu naught is on the top side, means numerator side. So here it is just ulta. So I hope you understood the energy density and the energy stored in an inductor. Thank you.